Japan's bullet train, the world's first high-speed railway. Still the most technologically advanced in the world. In its life, it's shifted the equivalent of the entire population of the Earth at nearly 200 miles an hour.
The Japanese high-speed train is very different from a normal train. You don't just add a more powerful locomotive. It doesn't even have a locomotive in the traditional sense. A normal train can't stand the stresses of high speeds. You need to redesign it. In fact, along the way, you'll need to reinvent the wheel. And that called for some surprising engineering connections. The bullet train wouldn't have been possible without
Ancient chariot racing.
Oh, my God!
Yeah, eat your heart out, Ben-Hur. A crowbar. A medieval clock.
Oh, that really is moving. The stopping's going to be uncomfortable, obviously.
A 19th century luxury car.
My wheels on my train just can't get enough grip to get me moving.
And the electric telegraph.
Any sign of an earthquake?
Yeah, there's something coming in.
Right.
Japan, a rugged land of volcanic mountains and devastating earthquakes. Most of the population is squeezed into some of the largest cities on the planet. Getting around the country is a challenge. Space for roads is restricted, and to move all the travelers by air, 3 jumbo jets would have to take off every 5 minutes. So the Japanese chose the train for mass transport. They transformed the humble train into an iconic and sophisticated engineering marvel.
This is the N700 bullet train, latest in a line of pioneering high-speed trains. And, well, it even looks fast, which it is. Close on 200 miles an hour, 300 kilometers an hour in regular service. But if you think it's all about what happens here at the pointy end, you'd be wrong. It's much more radical than that. The whole thing is a system designed to get up to speed, then to corner safely and comfortably, even to stop automatically if there's an earthquake. It is quite a train.
How do you turn a normal train into a bullet train? It starts with the simplest thing: the shape of the wheels.
You would think the one place where a wheeled vehicle would have no problems at all is a straight piece of track like this. I mean, you've got wheels, rails, no bends. What can possibly go wrong? In fact, everything can go wrong if the wheels are the wrong shape. I mean, it's still round. Round is good in a wheel. But it's the part that touches the track here that makes contact. That is absolutely critical. Without the help of a medieval clock, a high-speed train could simply throw itself off the rails.
No need to take my word for it, because I've brought my very own carriage to the Hammond Railway's proving ground for its inaugural journey to test its wheels. It's not a grand design. It doesn't even have its own power, but that doesn't matter, because I've got a powerful winch to drag it along this dead straight piece of track at speeds up to 50 miles an hour. Unfortunately, Hammond Railways don't stretch to basic amenities, like seats.
That's one of the reasons why I won't be riding on my carriage. The other reason is, well, it doesn't have any brakes. I did say it was basic. It'll be brought to a complete and probably quite sudden halt by that barrier down there. On the plus side, this does have everything we need to show just what high-speed train engineers are up against. Namely, we've fitted it with these train-style wheels.
They're exaggerated, yes, but just like real train wheels, they're conical, angled where they rest on the track. They might look pretty odd, but according to Paul Allen, an expert in wheel dynamics, they'll show clearly what happens to real trains travelling at speed. Finally, Hammond Rail is offering a feature never before seen on trains: basketballs on poles. They'll show how the carriage moves. He's revving his V8 muscle car from 1970s. There he goes. As it speeds down the track at about 40 miles an hour, the carriage starts rocking from side to side. It's called hunting oscillation.
I can see. Is that why the
Yeah,
the top of these posts are moving side to side?
Yeah, you can see it hunting a bit now.
That's not gone at all well for it, has it? That's a bad thing. The kind of thing you need to avoid in a real train.
And this isn't just a problem for Hammond Rail. Real trains have derailed on straight track, and the repeated sideways movement can also damage the track itself, like this one in Germany. Wobbling along a dead straight track is the fault of those cone-shaped wheels. So they don't seem like such a good idea. Why aren't they flat?
Well, the problem with flat wheels is we need to get round a curve.
Yeah.
So if we try and do that with flat wheels,
Right.
I've got my flat wheel here. We run it down the track.
See, it works. It doesn't work. It doesn't
not so
work.
much.
Yes, but we all know train wheels, they're round, but then they have like a flange on them that keeps them in the track. Flanges are the metal lips that sit down the side of the tracks.
We could put flanges on the wheels, but the trouble is then the wheels will be guided around the curve purely on these flanges, and we'll wear them out, and we'll wear the sides of the rails out. They'll all be wrecked
Very quickly.
very quickly, yes.
So, it's back to those conical wheels.
Someone clever came along and thought, well, if we put some cone angles, then we might be able to get this to go around the curve.
Go on then. Somebody came up with this.
Okay, so it's off. That's where the other one got to. And it's just... Well, it works.
It works.
Clearly. And that's just its shape.
Exactly,
It's sending it round.
A cone rolling on its side turns in a circle, and train wheels use this principle. As it goes round a bend, the train is thrown out, and the outside wheel effectively gets bigger, making a sort of cone which turns the train. But because conical wheels can effectively change size, they can make trains unstable, even on straight track, causing that hunting oscillation we saw, especially at bullet train type speeds.
The solution is an engineering compromise. So what we try and do is we get just the right amount of cone angle to get us around the curves we need to get round, but no more than that.
So there will be an optimum amount of slope, cone,
Yes.
for a train that's going to go faster.
Yes, so very high-speed trains have very low amounts of cone angle or conicity, and slower trains have much more conicity.
So the slope on a conventional train wheel is flattened for the bullet train. The angle is halved. Each wheel is precision machined to the perfect angle. And what's good enough for a bullet train is good enough for Hammond Rail. I'm exchanging my extreme conical wheels for flatter ones. I've also added some weight to try and stop it derailing again. I'll admit, Hammond Rail doesn't offer a complete service yet. No return tickets. You have to push yourself back to the station. Inconvenient, but cheap. Here he goes. So what we're looking for here is a steady ride.
Nice ride. No hunting.
That's perfectly happy.
That is going quick, actually.
God, that really is moving.
The
stopping's going to be uncomfortable, obviously, in a real situation.
The flatter wheels have eliminated hunting oscillation. Look how steady the basketball telltales are. My carriage travels straight and true on the rails, which means it can go really fast. But still nowhere near as fast as a bullet train. For those kinds of speeds, the engineers couldn't just rely on flatter wheels to avoid hunting oscillation.
They needed a two-part solution. The second part of which lay at the heart of a medieval clock.
Before clocks were invented, time was pretty fluid, but medieval monks wanted regular prayer times. They needed precise clocks.
And that particular prayer was answered for them around the middle of the 15th century with the invention of a new type of clock. And the device that transformed clockmaking, monastic life, and ultimately the bullet train was this, the coiled spring. There's one in here, in this clock as well. All it does, as you wind it, it coils itself around itself tighter and tighter, and that's storing energy. Then as it unwinds itself slowly, that energy is released, and it's that energy that's used to turn the gears and cogs that turn the hands and tell us the time. And with a little bit of tweaking, this horological motor would go on to help solve the problem of hunting oscillation on the bullet train.
Because coiled springs are also good for suspension systems. By stretching and squashing, they smooth out bumps in the road, as car mechanics discovered in the early 20th century.
And train engineers adopted the same idea. Coiled springs, in fact, are particularly good for trains because they don't just absorb up and down motion, they also dampen side-to-side rocking. On the bullet train, coiled springs absorb the energy of the hunting oscillation. Stiffer springs absorb more energy, so they dampen the sideways movement, so the train can't rock as violently. Right, they are actually building trains here, so I'll get out of their way.
Thanks to some punctual monks and clever watchmakers, the engineers were able to design a train undercarriage that stops it hunting, shaking from side to side at high speeds. With flatter wheels, the train rolls so straight that it wears an almost perfect line along the rails. The machining of the wheels is the beginning of the journey for the bullet train. It ends up like this, a brand new bullet train. And once built, it's ready to take its first high-speed journey. I wonder if they've left the keys in.
Here it is, the business end. I'm guessing flat out. What, close to 200 miles an hour, 300 kilometers an hour. Being a train driver is quite exciting again. This might be in the workshop, but it is actually wired up and ready to go. It'll be driven out of here. But not now, not by me.
Probably just as well they didn't leave the keys. But what happens when you do switch the train on? To move at all, let alone reach breakneck speeds, the bullet train needs power. And it gets all the power it needs in the form of electricity from overhead lines.
The connection between the wire and the train is this device along here, the pantograph. So electricity flows in through those few square centimeters where it touches the wire, and from there, down into the train.
To feed enough power, engineers faced a choice between a faster or a bigger electrical flow, stepping up the voltage or boosting the current. In a lab that looks more like the set of a sci-fi movie, Manchester University professor Ian Cotton shows the demands big currents make.
So Ian, talk me through this. I'm guessing current is going to go around there somewhere.
Yes, we have a transformer from the mains, and in this loop we get a high current.
All right. Well, fire it up then. Is it working now?
It will do. You'll see the numbers on the ammeter go up, so that means we're getting more current flowing through the loop.
So this is the quantity of amps flying through here. Oh, hang on, look already. This wire is getting hot. What's happening?
High amps, a big current, overload the thin wire. It heats it up to the point of complete failure.
So if you have very, very high current, you need to use a very big piece of metal to let the current flow.
So for our train, we'd need much bigger than this.
Absolutely, it would be very, very big and very, very heavy.
To carry enough current for the bullet train, the overhead wires would have to be huge, thicker than a man's arm, and enormously expensive. Totally impractical for train lines that run for hundreds of miles. The only other way to give the train the juice it needs was to up the flow, the voltage. Train lines usually carry 1,500 or 3,000 volts, nowhere near enough for a bullet train, so the engineers increased it to 25,000 volts. But with such a gigantic voltage, any break in the circuit between the wire and pantograph can be catastrophic.
The pantograph has, well, just one job really, to maintain that contact with the wire overhead. But it is quite an important job because lose that contact and you lose power, which would be inconvenient.
Worse, you might damage the train. If the pantograph loses contact, it causes an arc. In the safety of a high-voltage lab, an arc looks very pretty.
Woo! So what are we seeing here?
So this is something called a Jacob's ladder, and we're making a high voltage arc which is travelling up.
Arcing happens when there's a break in a high-voltage circuit. In a Jacob's ladder, there's a gap in the circuit between the two poles. The voltage is so high that it turns the gap into plasma, superheated air. And plasma is very hot, close to 10,000 degrees C, making arcs very dangerous indeed.
That's arcing that we're looking at.
Exactly, so that's what would happen if the pantograph moved away from the actual wire.
Arcing does happen on normal trains. Here, icy overhead wires are breaking the circuit. But the higher the voltage, the more arcing is a problem. In this demonstration, I'm going to play the pantograph to see what happens to my paper train when the connection is broken.
So this is a demonstration of the potential bad side of high voltage.
Yeah, so the copper bar is at high voltage, and if you touch that pole to it and move it away, you'll make a high voltage arc.
Okay. There we go. But when it gets near to things... Aha! Yeah, straight away that's... Do you know, I can see the downside there. What's happened is it's set fire to my train quite badly.
Okay, so it's no surprise that the plasma arc ignites a paper train, but it can also damage a real train and its overhead wires. To prevent damage that could take whole lines out of action, the engineers needed a pantograph that would not lose contact with the overhead wire.
And the key to their solution lies in this. It's just a crowbar. Well, a lever. And used in the right way, it can keep the pantograph pressing against the wire no matter what.
Which is a good thing, because you really don't want to mess about with dodgy connections and massively powerful electrical supplies.
Levers are essentially pretty simple devices. There's something long, like this, that pivots around a fulcrum, like that.
The longer the lever, the more it can lift.
So, to move something heavy like this anvil, I'm going to need a longer lever. Yeah, that should do the job. In place, and, well, that's easy. It was the Greek scientist Archimedes who first worked out the significance of the distance between fulcrum and where the force acts on a lever. He reckoned, rather famously, that with a long enough lever he could move the Earth. Though he would, of course, have needed somewhere to stand to do it.
The bullet train's unique pantograph acts like a lever too. A spring pulls the pantograph up. If the spring contracts, it pulls with less force. To compensate, a cunning mechanism automatically lengthens a lever, increasing the force.
The whole thing is a compensatory mechanism, and the result is a constant pressure against that wire.
And so far, they've been able to keep the train supplied with high voltage power without frying the pantographs. With power on board, the engineers faced their next challenge. How to convert the power to speed. And in particular, how to make a train fast from a standing start. It needs the right balance of power and grip.
Making something fast isn't just about making it more powerful. You need to consider its weight too. Light is good. That's why they don't make fast cars out of lead, you may have noticed. But here's the thing. You can make something too light.
If a vehicle's too light, it can't grip the ground enough to get traction, which is how things like cars and trains turn engine power into movement. Without traction, you're not going anywhere, no matter how big your engine. To demonstrate, I've created my own train and a very slippery track for it to run on.
Yeah, well, as I think you can see, no matter how much power I use, no matter how much oomph I give it, and I'm giving it plenty, my wheels on my train just can't get enough grip to get me moving. In fact, sometimes the more power I use, the worse it gets.
My train doesn't have good traction because it's too light to grip properly. Of course, wheel trains don't run on skid pans, but they too can suffer from not having enough traction.
One way to improve traction is to increase weight, especially if the added weight is over the driven wheels, which in the case of this pickup is the rear wheels here at the back. All of which means that lot needs to go in there. So carry on, I'll be here. Isn't it great when everyone pulls together? Team effort. There we go. The last bag in place. I did all of that there. Those bags then, the weight right over the driven wheels at the back of the truck. Time to test it.
We have added about half a ton above the rear axle. No contest. Same skid pan, more weight, better grip, better traction. But the last thing you want to do to a train designed for speed is add weight. Instead, bullet train engineers found the solution to their traction problems in an early luxury racing car, the Lohner Porsche. In 1899, Ferdinand Porsche, that Porsche, designed a pioneering car in which each wheel was driven by a separate motor, the first four-wheel drive. And as off-roaders the world over know, with more driven wheels, you get better traction.
I'm going to need to modify this vehicle. Right, that's done. This truck is now four-wheel drive. More wheels driving, it should grip. And it does.
Making all four wheels driven means better traction without added weight. And the Japanese did exactly the same with the bullet train, flipping the traditional train around completely.
Conventional trains use locomotives, big, heavy powerhouses that pull or push the other carriages along. But the bullet train engineers have kind of turned that principle on its head, because the pointy carriages at the front and the very back of this train have no engines. Instead, all the other carriages do. It's called a multiple unit system, and on this train, 14 of the 16 carriages have their own motors. In here, each motor drives 2 wheels, so it is, by my reckoning, 112-wheel drive.
Good traction without the extra weight means it can accelerate suitably quickly for a bullet train. All thanks to a 19th century 4x4. The next challenge for the engineers was how to keep that speed up round corners. Cornering too fast is a problem for any vehicle. This is Dave. He and his motorcycle sidecar are going to be the guinea pigs in my new challenge.
This, by the way, isn't just an awkward-to-get-at refreshment system. This water is part of the experiment. It's science. Take it away.
Can Dave and the drinks complete my slalom course?
Now we come to the first turn. Here we go.
Dave and I go one way, and the drinks go the other.
I'm going to be thirsty. I mean... Dave? Saw my drink's gone. No big surprises there, OK, but in the interest of science, we must dot the I's and cross the T's. We all know the feeling, if you've ever been around any sort of corner at speed, when you feel you're being pushed to the side. It's called centrifugal force, and basically it's because your body as an object, wants to carry on going in a straight line, but the car, or bike, is pulling you that way. So relative to it, you feel a force throwing you that way.
And centrifugal force can have deadly consequences. In Osaka in 2005, a commuter train took a bend too fast and flew off the tracks. 107 people died. Thankfully, derailment is rare. But tight bends and high speeds produce strong centrifugal forces. Bullet train engineers didn't want to slow the trains down. To get round the problem, they turned to some of the very first wheeled vehicles. Chariots. Ancient charioteers knew how to corner quickly without flying off track, and so did their modern counterparts. This is a modern chariot, a scurry. Jeff Osborne is our Ben-Hur, and these are his ponies, Zig and Zag.
So what am I going to
Well, what
do?
you're going to do, you're going to keep the cart stable.
I thought I was just sitting a bit of passenger. I was going to bring a book.
No, you're not going to read a book. You're going to lean this way and lean that way.
So if I get it wrong...
We'll roll over.
These modern charioteers race around twisty courses with lots of cornering. And to keep the scurry stable, usually Alison sits on the back and leans into the turns. But today, I'm doing it. No pressure then.
Never let go. If a pony trips, you'll be straight out the back.
Bad. So, 1, 2, lean. 1, 2, lean, and I lean the way
As
and
far
then
as
into
you
the
can.
turn as far as I can
Yeah.
go.
If the wheel starts coming off the ground, you lean further.
So, after that, frankly, terrifying briefing, we're off.
This is nice. I like this speed. This is fast.
Leaning into bends reduces the centrifugal force that pushes us outwards. This balances the carriage and allows Zig and Zag, like their ancient counterparts, to corner faster. It's a technique first recorded by ancient Greek author Homer in his epic account of the Trojan War, the Iliad.
ancient charioteers couldn't possibly have known about the Newtonian laws of inertia and centrifugal force. How could they? They hadn't been invented yet. But somehow they instinctively knew that leaning helps you turn faster. I'm sure it looks lovely, but it's really frightening.
But what about my prototype mobile bar? To see if leaning is the key to success, I fired Dave and drafted in Frank.
So, I am going to try this again. I am determined to crack my motorcycle mobile refreshment system solution. And I'm going to use this, which is a rather different motorcycle and sidecar outfit, because this one tilts. I'm ready, sir.
This sidecar tilts instantly and effortlessly as it corners, keeping my drinks firmly in place.
That is astonishing!
Ben-Hur was clearly onto something, though I'm pretty sure he never foresaw its impact on mobile refreshment systems.
Science works! Who'd have thought?
So, the more they lean, the less the force pushing outwards on sidecars, chariots, and trains. To make trains lean, tracks are banked, inclined into the bend. And that worked well for older, slower trains. But bullet trains are so fast, they need to lean even further into bends. Bullet train engineers didn't need to wait for reports from uncomfortable passengers to know that banking alone isn't enough. This simulator can replicate the sensations of the bullet train travelling at any speed, on any kind of track. Today's experiment, cornering at nearly 200 miles an hour.
Right now, going in a straight line, and I'll admit I'm completely convinced, as far as I'm concerned, I'm in a high-speed train. And as we go into the bend, this has been set up to simulate just a banked track. I think it's starting to, yeah, I can, oh, yes, straight away. Yeah, I can feel that throwing me off to the right. So banking isn't enough. And you can't bank the track any more than this, because if you do, well, if a train has to stop at it one day, it might fall over.
Which is where Ben-Hur comes to the rescue. Computer-controlled airbags under each carriage make the entire bullet train lean. As it corners, each section of the N700, the latest bullet train, tilts independently at just the right time and by just the right amount.
On a real bullet train, the effect is quite noticeable. Or, in fact, it isn't. And that's kind of the point, isn't it? Because right now, judging by the blur through the windows, we're doing the kind of speeds that present a bit of a problem for my tea if there weren't some controlled tilting taking place. In fact, I'm so confident I'm going topless. This would be potentially dangerous without a very clever train. Look at that, I mean, it's not going anywhere. What if Ben-Hur was a tea or a coffee man? No, he was coffee, I'm sure.
Thanks to ancient charioteers, bullet trains corner 12 miles an hour faster, keeping travellers right on time. So, bullet trains stay on track, along straights and around bends, as long as the track itself stays in place. But you can't bank on that here, as recent events show.
All trains face a big problem in Japan. Earthquakes. This is one of the most earthquake-prone lands on the planet. And the problem could be much worse at higher speeds, because trains and passengers could potentially suffer much greater impacts. Equipping their high-speed trains to stay on track through an earthquake would be a particular challenge for the engineers.
Japan is struck by around 900 quakes a year. In March 2011, An earthquake measuring 9 on the Richter scale, the largest ever to hit the country, struck Japan. The earthquake's epicenter was 80 miles out to sea, but it triggered a massive and hugely destructive tsunami. To date, more than 25,000 people are dead or missing. Earthquakes in Japan pose a real challenge to architects and engineers.
Of course, the thing that really worries railway engineers is the same earthquakes that topple tall buildings and rip up roads can derail trains. So it's good to know that thanks to the electric telegraph, there is a system in place to protect passengers on the bullet train.
Engineers needed advance warning of earthquakes to slow the trains. So they designed the world's very first earthquake warning system. The idea was to alert engineers before a quake arrived. But in actual practice, this proves to be a problem. An earthquake warning system is really only as good as the tremor detectors or seismometers. To understand the problem, we need an earthquake. And back in England, you can wait all day for one to come along. But according to earthquake expert Hugh Hunt, a lake and a large weight will replicate the key components of a seismic shock. And a precarious tower of blocks will play the part of its potential victim.
Right, Hugh, we've assembled everything you asked for. We're in a boat on a small lake, and over there is a digger with a big weight in it. How's this an earthquake?
Well, we can simulate an earthquake by dropping this lump of metal into the water, and it's going to create a wave. And in an earthquake, you've got waves in the ground.
Hugh has set up a system to warn me of the quake before it strikes, so I can try to protect the tower. It all depends on this.
That thing there is a seismometer. It measures motion.
Hugh's seismometer should detect the quake and trigger a warning on his laptop.
So we have an earthquake detection system down there attached to my tower.
Yeah.
So it's going to know when there's an earthquake.
I'm going to use my earthquake detection system to tell you when you have to take action to protect the tower, right? So
This is my earthquake
That's the earthquake protection system. Okay, Richard, ready for an earthquake?
Yeah, I am, yeah.
Right, so I'm going to ignore the sound of a large weight dropping into the water 20 meters away from me. I won't move until Hugh's warning system detects the quake.
Okay, earthquake, go!
Any sign of an earthquake?
Yeah, there's something coming
right,
now.
right. Yeah. Do you see, the thing is...
You're too slow.
Well, how am I possibly going to... All you did was say there's an earthquake
You're
happening.
too slow.
But there was an earthquake, then it fell
Look,
over.
it went red here, okay?
But I was with my protection system, I never used it.
Red means earthquake, Richard, and you were just too slow.
Yeah, clearly what we have there then is a problem.
Hugh's system only detects an earthquake when it's arrived. Not much advance warning, not much good. Luckily for bullet train protection, earthquakes aren't quite as sneaky as this. They actually announce their arrival with small, fast-moving waves.
And what they discovered back in 100 and something years ago was that there's two waves, a primary wave, which they called the P wave, and a secondary wave, which they called the S wave.
The slower S waves are the destructive ones that topple cities and floating towers. They're what Hugh's seismometer detected, but too late to be a useful warning. The key to advance warning is to detect the faster P waves. But unfortunately, P waves are much smaller than S waves. You need a more sensitive seismometer. And for them, you need electromagnets, first used in the electric telegraph way back in 1837.
This is a working model of a device that quite probably represents the very first use of electricity for, well, anything. And it's actually a machine used to communicate between railway stations. Central to it is electromagnetism.
Behind the metal needles are coils of wire. Passing a current through a coil turns it into an electromagnet, which moves the needle. Reversing the current moves the needle in the opposite direction.
If I pass a current through the coil, the needle moves. If I switch it and pass the current the other way, the polarity switches, the needle moves the other way. All I needed then was a map of letters, and you can point to them if I want to spell an H or an I or a K. If I want to do an E, point both needles. Hasn't got all the letters, there are only 20 on here, so it's an early form of texting.
150 years later, the electric telegraph has made way for mobiles and the internet, but electromagnets are still very useful.
This isn't a telegraph machine, obviously it's a crane, quite a big one. But the important bit is at the business end there, because it's an electromagnet. There it goes doing its thing. Basically, this is just a magnet that can be on, or at the touch of a button, off. Suddenly it's no longer a magnet. But it isn't always that simple, because it can be a question of degree. It can be powerful or less powerful.
You can vary this crane's lifting power. Small current, weak magnet, less lift. Up the current and you can shift large lumps of metal. But that's not all. You can measure changes in electromagnetism very accurately, and knowing how much force is being used is the key to protecting the bullet train. And, I hope, my tower from earthquakes. Back on the lake, I'm going to update my earthquake warning system. This time, sensor expert Sean Gosen is coming aboard with a sophisticated electromagnetic seismometer.
So, Sean, you came aboard bringing with you your posher piece of kit. What essentially is the difference between... This is the real deal, isn't it? This is...
Yes, it's much more sensitive.
Sean's seismometer uses electromagnets to detect tiny movements, such as the pulses of P waves.
So will you be able to detect these finer P waves that Hugh singularly failed to do? Well,
Thanks, Richard.
Well, your earthquake warning system consisted of saying there's an earthquake and everything's fallen over.
Sean's seismometer is so sensitive it needs to be placed on the stable lake bed.
OK, well, if everybody's in the right place, we'll give this a go. I promise not to look. I'll just wait until I get a warning from Sean.
We're both monitoring our system.
Yeah.
Are we ready for an earthquake? Go!
Okay, Richard.
I've deployed my system. That is an early warning. Look at that. Oh!
Richard, here comes an earthquake!
Yeah, thanks, Hugh. We know there's an earthquake because everything's moving, but it's OK. I think my earthquake protection net has saved the day, and it was only able to do so because you could actually warn me there was an earthquake coming this time, rather than you could tell me there is one. And it's that difference, that it's just the fact that your system can detect those finer, smaller, different frequency waves.
Sean's system alerted me about 7 seconds before the quake arrived, an actual advance warning. And seismometers using electromagnets are also sensitive enough to protect the bullet train. The current system is the most sophisticated earthquake warning system in the world. About 70 linked seismometers along the track and nearby map seismic activity. 2 seconds after detecting P waves, power is switched off and any train in the danger zone automatically brakes. For vehicles with a stopping distance of nearly 2 miles, every second counts. The March 2011 earthquake destroyed stations, tunnels and bridges up and down the bullet train network. But crucially, not a single bullet train was affected, because the earthquake warning system automatically brought them to a halt. In some cases, 15 seconds before the tremors damaged the tracks. But what happens if there's no time for the brakes to kick in? 7 years earlier, one train was so close to the epicenter of an earthquake it was derailed. The only time this has ever happened. This prompted engineers to develop a cutting-edge anti-derailment system. This is the Bullet Train Research Centre. They don't let just anybody see their pioneering kit, and I'm shadowed at all times. Ah, hello.
おはようございます。村松と申します。
Yes, hello.
今日よろしくお願いします。
Very nice to see you.
どうぞ。
Ah, right, sit down.
はい。
Okay, this is where I'm going to find out all about the
じゃ
place. The engineers were keen to share the complicated earthquake science behind the system, but it's all Greek, well, Japanese to me.
クラスでもう一度揺らしてみます。映像を次にご覧いただきます。
Yeah, I should have brought a phrase book there. Fortunately, the lesson has a practical demonstration for underachieving students like me. It's one of those simple but effective solutions. They've fitted an extra rail. So in the event of a train being caught too close to the epicenter of an earthquake for the P-wave system to detect it and warn the driver in time to slow it down, this is here to keep everything on track. Even when the ground moves violently, the wheels are held in place by the extra rails. As with every part of the bullet train, it's been exhaustively tested. To find out if their idea worked, the engineers built themselves, well, it's a model train set. Admittedly, the track doesn't go very far, but then it is built for a very specific purpose. This is a 1/5 scale replica of the real thing. And it has a feature that probably most model railway enthusiasts don't have on their set at home, an earthquake simulator. The lip of the wheel sits between the two rails, so even the really violent tremors can't shake this train off track. The special rails are currently being introduced along sections of the line. It really is an astonishing train. Fast, earthquake-proof, always on time, and beautiful too. Bullet train engineers have moved technology pioneered in Britain 200 years ago into the 21st century. Now, bullet train technology is being exported all over the world, even back to Britain. The bullet train really has led the way to a new global age of the train. China and America are committing to high-speed rail networks. And this remarkable, revolutionary train wouldn't have been possible without ancient chariot racing. Oh my God! A crowbar. A medieval clock. God, that really is moving. The stopping's going to be uncomfortable, obviously. A 19th century luxury car. My wheels on my train just can't get enough grip to get me moving. And the electric telegraph.